Good day, everybody. How are you all doing? Today, we are going to talk about chapter 6.3, sampling distribution for proportions. So without further ado, I'll get started. So we are going to talk about central limit theorem for proportions. Construct the sampling distribution for a sample proportion. Use central limit theorem to complete probabilities for sample proportions. Construct the sampling distribution for a sample proportion. That is our objective 1. In a population, the proportion who have a certain characteristic is called the population proportion. The population proportion is denoted by P. In a simple random sample of n individuals, let X be the number in the sample who have the characteristic that we are looking for. The sample proportion is given by P with a thing at the top called P hat. And it is X number of successes, number of people who have the characteristic in a sample of size n. So P hat is given by X over n. Here is a good example. A computer retailer wants to estimate the proportion of people in her city who own laptop computers. She cannot survey everyone in the city, so she draws a sample of 100 people and surveys them. It turns out that 35 out of 100 people in the sample own laptops. So the sample proportion is P hat is given by 35 over 100. The proportion of people in the entire city who own laptops is the population proportion P. Now, this retailer drew a random sample of 100, and out of that random sample, 35 have laptop computers. So 35 is X, the number of successes, and N, the sample size is 100. Suppose she draws another sample, random sample of 100 of the city residents and find out that 40 of them have laptop computers. In that case, P hat will be 40 over 100 or 0.4. Now she can draw many samples of size, simple random samples of size 100 from that entire population. Suppose she draws 50 samples, each of size 100 from that population, and ask each of these 50 samples of size 100, how many of you have laptop computers? So first she got 0.35, next she got 0.44. The third one, maybe 45 out of 100 have laptop computers. So that value of P hat will be 0.45. So she will have 50 values of P hat. So now she can divide those 50 values of P hat into groups of equal width. The P hat will be represented on the horizontal axis, different groups of P hat. And on the vertical axis will be relative frequency. So for example, the first group may be between 0.3 and 0.35. Okay. And let's assume that the height of that or relative frequency of that group is 0.25. What does it mean? It means 25% of the 50 samples, okay, each of size 100, 25% fall between 0.3 and 3.5. Okay, so 25% of all those 50 samples are between 0.3 and 0.35, or the sample proportion fall between 0.3 and 3.5. So we can draw a vertical rectangle on top of the group between 0.3 and 3.5, and the height of that rectangle will be 0.25, which is the relative frequency or probability, or what proportion of those 50 samples the P hat is between 0.3 and 3.5. So similarly, we can draw other vertical rectangles on top of the different groups, and we can join the top of these groups by a smooth curve. This is the sampling distribution of P hat. Sampling distribution of p hat. So in sampling distribution of p hat, you have probability of relative frequency on the vertical axis and the values of p hat on the horizontal axis. Okay. So here is the example that I was just talking about. The big rectangle is the entire population of city residents. And the ovals inside the rectangles are different samples of the same size. And there are different values of p hat, as I said, 0.3, 0.35, 0.4, 0.45. You can divide these 50 values of p hat in my example into 50, say you can divide it into 5 or 6 groups, and on top of each group you will draw a vertical rectangle. The height of the rectangle will be equal to the relative frequency. So if several samples are drawn from a population, they're likely to have different values for p hat. Because the value of p hat varies each time a sample is drawn, p hat is a random variable. Why it is a random variable? Because beforehand we do not know what will be the value of p hat. So it's a random variable and it has a probability distribution. That means p hat on the horizontal axis, on the vertical axis is relative frequency or probability. The probability distribution of p hat is called the sampling distribution of p hat. Consider tossing a coin 5 times. This produces a sample of size n equal to 5, where each item in the sample is either a head or a tail. The proportion of times the coin lands on heads is the sample proportion p hat. The probability that it lands head each time is 0.5. Therefore, the population proportion of heads p is equal to 0.5. Next, we look at all 32 possible samples that can be constructed. Why 32? Because we are tossing the coin 5 times and not every time we are going to get head. So these are the 32 possibilities. For example, the first one, look at the first one on the top left corner, T, 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 T. That means in all the 5 tosses, we got tail and none heads. So the sample proportion of heads in that particular sample is 0 because there is no head. In the next one, there is only 1 head out of 5. So the sample proportion is 0.2 and so forth. This table displays all possible samples of size 5 and their sample proportion p hat. Now, if we add all the values of p hat in this table, columns, so take the p hat values from the column with the title p hat, okay, and add all those p hat values and divide by 32, you will find the mean of all those p hat values is mu p hat is 0.5, which is same as the population proportion. P is also 0.5. In the long run, you expect 50% of the time you'll get heads. So P is 0.5, mu P hat is also 0.5, which is equal to P. The standard deviation, we can of course put it in the calculator and calculate the standard deviation of this population of size 32 is sigma P hat is 0.2236. Next, we compare these values to the population proportion 0.5 and the sample size 5. In the previous table, the mean of the sampling distribution mu p hat is 0.5, which is the same as the population proportion p is equal to 0.5. This relation always holds. The mean of the sampling distribution of p hat is denoted by mu p hat and equals the population proportion. So mu p hat equal to p. The standard deviation of the sampling distribution is sigma p hat is 0.2236. It is not immediately obvious how this is related to the population proportion and the sample size n. Note, however, that sigma p hat is equal to 0.2236 is equal to square root of 0.5 times 1 minus 0.5 by 5. So what is the relationship of sigma p hat to p and n? Remember, p is the population proportion, which is 0.5, is sigma p hat equal to square root of p times 1 minus p divided by n. The standard deviation of the sampling distribution of p hat is denoted by sigma p hat is sigma p hat is equal to square root p times 1 minus p divided by n. So we have to remember the sampling distribution, its mean mu p, sampling distribution of p hat, its mean is mu p hat equal to population proportion, that is p, and sigma p hat, which is the standard deviation of the sampling distribution of p hat, is given by sigma p hat is equal to square root of p times 1 minus p divided by n. The soft drink cups at a certain fast food restaurant will have tickets attached to them. Customers fill up the tickets to see whether they win a prize. The proportion of tickets that are winners is P equal to 0.25. A total of N equal to 70 people purchase soft drink between noon and 1 p.m. on a certain day. Let P hat be the proportion that win a prize. Find the mean and the standard deviation of P hat. Remember, mean of P hat, mean of sampling distribution of P hat will be mu P hat equal to P equal to 0.25. How about sigma P hat? It's given by that big formula. So how do I do it in the calculator? I first I'm calculating sigma P hat. So I press the second button on the top left and then x square, which is in the first column halfway down, is x square. I press that one. That gives me a square root on my calculator key. Okay. And then inside the square root, I first press 0.25, which is the value of P. I do not have to put a multiplication sign after 0.25. I straight away put a left parenthesis. And then inside that left parenthesis, 1 minus 0.25, just like as it is written on the slide. So second x square gives me the square root, then P is 0.25, left parenthesis, 1 minus 0.25, and then you have to put the right parenthesis, and then you have to divide it. So press the divided by sign after that, 70. Why 70? Because that is the value of your sample size, n equal to 70, and hit enter. And you get sigma p hat is equal to 0.05175, which they have rounded to 0.0518. Here is a problem. Calculate mu p hat and sigma p hat if n equal to 20 and p equal to 0.82. Now we know mu p hat is equal to p equal to 0.82. How about sigma p hat? First thing we do, press the second button, then x square in the first column. Gets the square root on the calculator screen. Inside the square root, first thing is p, 0.82. Then a left parenthesis, 1 minus 0.82. Close the right parenthesis, divided by sample size of 20 and hit enter. And the answer is 0.05891. That is sigma p hat value. Okay. Probability histogram for a sampling distribution. Probability histogram for the sampling distribution of p hat for the proportion of heads in 5 tosses of a fair coin is presented. We can see that distribution is reasonably well approximated by a normal curve. Okay, so that is the top curve. That is the top curve. Okay, so let me get rid of this. That is the top curve. Okay, so you have p hat. Oops, you have p hat in the horizontal axis. It doesn't move. Doesn't go back to the, yeah. Okay, so you have p hat in the horizontal axis and relative frequency or probability on the vertical axis. You toss the coin 5 times. Okay, that is the top curve. Okay, so p hat on the horizontal axis, relative frequency, probability on the vertical axis. Here the coin is tossed 5 times. That means n equal to 5. Now we make n equal to 50. The experiment is conducted again, but 50 tosses of a fair coin. As we increase the number of tosses, so n from 5, it became 50. The sampling distribution of p hat, which is the second curve now, bottom curve, is more closely approximated by a normal curve. So you see on the top n is equal to 5, on the bottom n equal to 50, but the curve for n equal to 50, the sampling distribution is more close to a normal and it has got a lower standard deviation. It's tall and thin. When p is equal to 0.5, the distribution of p hat is somewhat close to normal, even for a small sample size like n equal to 5. Remember, our population proportion is 0.5 in this case. What they're saying, if p is equal to 0.5, then even if you use a small sample size, like we did in the top curve, n equal to 5, it closely resembles the sampling distribution of p hat is a bell-shaped, okay? Because p is 0.5. However, if p is close to 0 or close to 1, we need a larger sample size, like n equal to 50, okay, before the distribution of p hat is close to normal. A common rule of thumb is that distribution may be approximated with a normal curve when n times p and n times 1 minus p are both at least 10, okay? So, I'm tossing the coin 5 times, okay? My p is 0.5. 5 times 0.5 is 2.5. That is not greater than 10. That's why the first curve on the top is not a good bell-shaped curve, not a well-looking bell-shaped curve. However, in the second case, when I'm tossing the coin, n equal to 50, 50 multiplied by p is 0.5, 50 multiplied by 0.5 is 25, and that is greater than 10. So we can have the sampling, represent the sampling distribution by a smooth bell-shaped curve, as in the second case, because n is 50 and n times p is greater equal to 10. We should also check n times 1 minus p. Now, I want to mention n times p is the number of successes. 50 times 0.5 is 25. Total number of tosses is 50. So number of failures is 50 because n is 50. 50 minus 25 is 25. That is n times 1 minus p is also 25, which is greater than 10. Hence, we get a smooth bell-shaped distribution for the sampling distribution of p hat when n is equal to 50. However, we do not get that when n equal to 5. We do not get a smooth bell-shaped curve. We now state the central limit theorem for proportion. The central limit theorem for proportions, let p hat be the sample proportion for a sample of size n from a population with population proportion p. If n times p greater equal to 10 and n times 1 minus p greater equal to 10, then the distribution of p hat, which is also called sampling distribution of p hat, is approximately normal, means bell-shaped curve, with mean mu p hat equal to p and standard deviation sigma p hat is equal to square root. Inside the square root, p times 1 minus p divided by n. Check your understanding. Decide whether it is appropriate to use a normal distribution to find the probabilities for p hat. A simple random sample of size 20 is drawn from a population with population proportion 0.7. So 20 times 0.7, which is number of successes, is 14. What is the number of failure? 20 minus 14 is 6, and that is less than 10. So we do not meet both conditions, n times p and n times 1 minus p greater equal to 10. Since we do not meet both the conditions at the same time, we cannot use a bell-shaped distribution. We cannot use a normal distribution, okay, to find probabilities for p hat. Let's do the second one on the top right. 55 times 0.8 is 44. That is your number of success is 44. So what is your number of failure? 55 minus 44 is 11. Both of the number of successes is 55 times 0.8 is 44, greater than 10. And number of failures is 55 minus 44 is 11. That is also greater than 10. Hence, we can use the normal distribution to find probabilities for p hat. Okay. Use the central limit theorem to compute probabilities for sample proportions. Okay. According to Harry's poll, chocolate is favorite ice cream flavor for 27% of Americans. That is, your population proportion p is 0.27. Hence, mu p hat, sampling distribution of p hat, its mean is equal to p equal to 0.27. And what about the standard deviation? Standard deviation is second x square in the first column. Gives me the square root. Inside the square root, p is 0.27, left parenthesis 1 minus 0.27, right parenthesis divided by sample size 100. So sigma p hat is 0.044396. Okay. Now you want to find what is the probability. So mu p hat, the center is equal to p equal to 0.27. Now you find out what is the probability. Sample proportion whose preferred chocolate is greater than 0.3. So you're on the right of 0.3. So your lower is 0.3, upper is a very large positive number, 1E99. So you go second, worst, number 2 is normal CDF, okay? And your lower, you're starting from 0.3. Your upper is a very large positive number on the right. So 1, first you type in the upper, and then second comma button on top of 7 button gives you the small capital E, which is exponent, which is 10 to the power of something, and we are going to type 99. So 10 to the power of 99 is a very large number, upper boundary on the right. What is your mean? Your mean is equal to population proportion, which is 0.27. What is your standard deviation? Is 0.05. Is it this one we're doing? Yeah. So they're going. Okay. So your mu is 0.27. Your upper is your lower is 0.3, upper is 1E99, and you want a greater than 0.3. So your lower is 0.3, upper is 1E99, your mean is 0.27. Your standard deviation you calculated before is 0.044396. You go to paste. Whenever you go to paste, you have to hit enter twice. And the probability is 0.2496. Okay. Approximately 60% of eligible voters voted in a recent US presidential election. P, population proportion is 0.6. Sample of 88, N is 88. So number of successes is 88 times 0.6, which is 52.8. Now number of failures is 88 minus 52.8, which is 835.2. Both of them greater or equal to 10. Hence, we can use a normal distribution to find the probability of p hat. Would it be unusual if less than half? So your p in the center, mu p hat is equal to p is 0.6, and you want less than 0.5. So 0.5 is your upper boundary, your lower boundary is a very large negative number. So second verse, before I do that, I should calculate the standard deviation of the sampling distribution. The standard deviation of the sampling distribution. Remember, sigma p hat is square root p times 1 minus p divided by n. So second x square gives me the square root. My p is 0.6. Left parenthesis 1 minus p is 1 minus 0.6. Inside the left parenthesis, then put the right parenthesis, divided by your sample size is 88, and then hit enter. It's 0.052223 as shown. Okay. Now you want less than 0.5. So second verse, go to number 2. You're starting from a very large negative number. So your lower is, you first press the minus button next to the enter. That minus. Then 1. Then second button, then comma button on top of 7, which gives you the E, 99. And your upper, you're stopping at 0.5. Your mean is 0.6. Your standard deviation you have calculated as 0.0522. How many places should you go? If you do 0.05222, you should be fine. And you go to 4, I went to 5 places of decimal, actually. Okay, 1, 2, 3, 4, 5. 5 places of decimal. Even if you had gone 4 places, won't make much difference. So you Bring the cursor down on paste and hit enter twice. And the answer is 0.0277. Okay. General Social Security Survey reported that 56%, P is equal to 0.56 population proportion of American adults saw a doctor for an illness during the past year. Sample of 65. So let's multiply 65 times 0.56 to find the number of successes. 65 times 0.56 is 36.4. That is your number of successes that is greater than 10. Now let's check the number of failure, which is total number of adults is 65, out of which the success is 36.4. So number of failures is 28.6. Both n times p and n times 1 minus p greater than 10. Hence, we can use the normal distribution to find probability for p hat. Okay. Now we need to calculate the sigma p hat, which is second x square gives you the square root. Inside the square root, p is 0.56. Then left parenthesis, 1 minus 0.56. Right parenthesis, divided by sample size 65 and hit enter. So it is 0.061569. Now you can round it off to 0.06157. That will be perfect. Okay. What is the probability that more than 60? More than 60 means you're on the right of 0.6. So second verse, number 2, normal CDF. You want more than 0.6. So you start from 0.6. Your upper boundary is a very large number on the right-hand side. So you first press 1, then second, and comma button on top of 7, which gives you the E, and then 99. Your mean is 0.56. And I have forgotten the standard deviation. So how will I can calculate it at this stage too. So I bring the cursor down on sigma colon, and to the right, the cursor is now flashing. Okay, here I can put in the formula. So second x square gives me the square root. Inside the square root, 0.56, then multiplied by left parenthesis, 1 minus 0.56, then close the right parenthesis, divided by sample size of 65. You don't have to calculate. You just put the formula here. What did I do? Sigma colon, then I put second x square, gives me the square root. With a parenthesis, left parenthesis, I did 0.56 for population proportion. Then left parenthesis, 1 minus 0.56. Right parenthesis, divided by 65. And the cursor is now flashing after 65. I bring it down with the down cursor key to paste and hit enter and enter. And the answer is 0.25795. Okay, 0.2580. Would it be unusual for more than 70%? So second verse 2. More than 70% means I'm starting from 0.7. So my left boundary is 0.7, lower boundary. My upper boundary is 1E99. My mu is 0.56. I'm not changing anything. My sigma has the whole formula on it. That's fine. I do not change it. I go to paste, hit enter once and then enter twice. And it is 0.0114, which is less than 0.05. Hence the event more than 70% is unusual. Why? Because its probability is less than 0.05. So yes, it is unusual. So I will stop here today. If you have any question, you can always shoot me an email and I'll get back to you as soon as I can. Thanks for watching, and I'm coming back next time with lecture for week 5. So take care. Have a nice day. See you next time.